forget about the physics, you forget about your knowledge, you just observe the process, and basing on the data, basing on your observation, you derive an empirical relationship describing it. And this is called also an inductive process. This is more general. When we say empirical, it's a term used by engineers. If I wanted to use a more general term, I would say that empirical formulas are inductive relationships. Inductive means that I start from observations and I travel back to the process. Deductive is the opposite. I start from the theory of physics, and I move forward to the description. Keep in mind that sometimes you can use both, and actually you should come to the same result, which is indeed true in many cases. There are several cases where, like dropping a pen, if you study the movement of the body with an inductive or deductive approach, you come to the same conclusion. So, as I said, and this is what you have to keep in mind, mainly we use empirical formulas. Okay? And if we use empirical formulas, we should find a way to describe their uncertainty. This is an order of magnitude more difficult. You find a lot of empirical formulas proposed by the literature for whatever problem of engineering, and especially in coastal engineering you can find really several empirical formulas. We will deal with many of them, but when it comes to the point of estimating uncertainty, and this is a problem, some relationships don't suggest you anything about uncertainty. And then you should keep it in mind very clearly. When you use an empirical formula, a lamp should turn on in your mind like, this is empirical, but what is the reliability of this formula? How can I estimate uncertainty? Okay, keep it in mind, because uncertainty very often is neglected by engineers and it leads to disasters. If you neglect uncertainty, it leads to disasters. Okay? So, if not disasters, it leads to a bad design. Sometimes it's impossible to estimate uncertainty. This is fine, but you have to be aware. You get an idea. You have to be aware that there is uncertainty, nevertheless. If you cannot estimate uncertainty, it's not a good reason to say there is no uncertainty. This is a big mistake. Okay? So, that's fine. Let's use the empirical formula and let's think about uncertainty. But, given that this process is a physical process, we can try to describe it by starting from the theory. And at least we can get a mixed process. It's possible. We can mix the two processes. If you start from the physics, you still have the problem of uncertainty. Okay? You get a physical equation describing a process. It looks like a deterministic relationship. It is not, because uncertainty is not eliminated if you use a theoretical approach. So even if you use a physically based approach, you have to think about uncertainty. So the same lamp should turn on in your mind. What is the uncertainty? And then you can use a mixed process, which means that you use an empirical formula, but you take advantage of your physical knowledge. So what did people that studied the longshore sediment transport do? Basically, they started taking observations. Remember, the scientific process, the scientific development, the scientific method always starts from observations. You observe something, and you want to describe it. Basically, you want to describe it in many cases because you need to describe it. So there is a social requirement, a requirement by humans to better understand what's going on, and then you turn it into a research question. This is the typical approach to science. And then there are several examples of scientific questions that were elaborated just for the sake of gaining knowledge. And this is something that is frequently debated, like people that study particle physics often have this problem that there are people asking them, and then once that you know the movement of a single particle, and then what's the benefit for humanity? So sometimes you know, the benefit may be just the knowledge, but very often we start from a societal requirement. Okay, that's fine. So, but in any case, we start from observations. So they started observing how beach developed, started collecting measurements of sediment transport. You may use traps in order to study sediment transport, sorry. And then they tried to understand how it works, and they proposed empirical formulas. We will see some examples. But they also proposed physically based formulations. And one of the most known formulas for estimating a long-short sediment transport is the CIRC formula, or CERC formula. And CIRC is an acronym, actually. It means, I don't remember, it's an acronym of I think, of an agency that started the process in the United States. I'm not really sure, but it's easy to investigate. And the CIRC formula starts from the knowledge of the physics of the process, and then of course there is some randomness there. And let's see how it works. There is, first of all, how do we measure the units? I mean, the long-short sediment transport. It may be expressed in cubic meters per day or year, so it may be expressed in volume over time or weight over time. And before we move forward, I wanted to give you some order of magnitude. This table that is on the web pages gives you some observations. These are observations of a long-shore sediment transport. You can also call it long-shore without the A. And it's in cubic meters per year. And these are some locations in the United States. So the whole table refers to United States, and here you can see the state from which you can understand whether it's the West Coast, the East Coast, etc. And you see that we are talking about several cubic meters per year, and from we may reach something like 500,000 cubic meters per year. You understand? It's something that is very relevant. And, okay, this is Atlantic coast actually, Gulf of Mexico, Pacific coast. In the lakes you have less sediment transport. What is the reason? It's easy to understand. The waves in lakes are usually not as relevant, not as important as in the ocean, of course. Okay, so again, let's go back to the CLC formula. So we can express the sediment transport again, volume over time or weight over time. It's easy to move from volume to weight, we will see it. There is a basic assumption in the CLC formula, which is written in the middle sentence. So the basic assumption is that the long-shore sediment transport rate, which means volume over time, for instance, rate means with respect to something else, which generally is time. So the sediment transport rate is related to the long-shore component of the energy flux that is transmitted by waves. Waves that approach, of course, the coast at an angle. So basically, what it happens is that you have the coast, we have the coast. Let me describe the coast as rectilinear. If it is not, what we do usually is to split it in small pieces in order to approximate the coast with a sequence of rectilinear segments. Now, for simplicity, let me assume that this is a straight line, okay? And then we have a dominant wave direction that is approaching. Let me identify the best working ones. It's approaching the coast at an angle. And usually we identify this angle. I don't remember what is the convention that I used, so let me define the angle later, okay? But it is an angle, it's not perpendicular. And of course you can identify this angle by making several different options. I wrote one, which I will introduce later. And then you have an energy flux that approaches the coast. And this energy flux, you know that it translates in a movement of mass. But given that it's difficult to relate the segment transport to the movement of mass, we assume that the segment transport is related to the energy that is transmitted by the wave. Why do we make this assumption? Why did they make this assumption? Because there is a clear relationship between the energy flux, the movement of mass, and the movement of segments. The energy flux is easier to describe once that you know the wave amplitude, once that you know the wave velocity, the group velocity. It's easy to compute the energy flux that is transmitted by waves. If you want to compute from the energy flux the flux of mass, this is very complicated. And therefore, the assumption was, in order to skip this step, the assumption is that we relate the long-short segment transport to the energy flux. So now we have to compute the energy transmitted by the wave. I think that Professor Archetti probably already introduced this computation to you. If this is the case, no problem. We compute it again, and it's a useful reminder. And let us, before I start, let's remind the component of the energy of waves. Let's remember about it. And I go back, I have a nice link here. I open this place, yeah. Okay, so we have here a wave, it's the red line. The red line is the wave, and then there is the green line, which is the kinetic energy, and the blue line is the potential energy. What I would like you to note is that first we can prove, we don't do that, but we can prove that there is a progress of potential energy and kinetic energy. They compensate each other. So basically you have a max of the potential energy at the wave crest and another max of the potential energy at the wave chest, at the wave through. You see the blue line, it starts from a max where you have the mean kinetic energy, which is understandable because when you get to the wave crest, the particle is just in steady state. It's not moving because the particle goes up and then gets to the top, and for a moment, for a tiny instant, the particle doesn't move. So you don't have kinetic energy. And you have the max potential. Why is that? Because you are at the max elevation. So if you consider a single fluid particle, it's at the max elevation, max potential, no movement, so zero kinetic energy. That's perfectly understandable. And then the particle goes down. and it gets at the mean sea level, the horizontal blue line, the horizontal black line, you see that it indicates time, but also indicates the mean sea level. So when you get to the mean sea level, you have the max of kinetic energy, because you have the max velocity of the particle, and you have the the minimum of potential. The minimum of potential, I'll explain you why, because this is something that is a bit more difficult to understand. Why you have the minimum of potential at the mean sea level. Now, the particle goes down below the sea level and reaches the wave through. At this stage, there is no movement. When you get to the lower part of the wave, no movement of the particle, no kinetic energy, and you have a max of potential energy. And this is difficult to understand, because we are used to relate the potential energy to position. So we understand that we get the max potential when the particle is up. We don't understand why we have again the max potential when the particle is down. Is somebody of you able to provide an explanation for this? Okay. And it's not just...
Because in that position, the particle has the maximum capability to go down or go up.
Okay. Okay, you're getting close. So you say you're getting close. It's a good explanation. But then I ask you, why is that? Because, so if I have a wave, I start from here, and then I get into this position, and you said, this is mean sea level. You said it's ready to go up. So it means even if it doesn't move, it's ready to go up. So it means that it has energy. So, but why is that? So what kind of energy?
At this point?
Yeah, at this point. What kind of energy? Because it doesn't move, no kinetic energy.
Potential. In the phase before.
Potential.
Yeah, it's potential. Yeah, but potential energy, when you say potential energy, I deliberately said it's related to position. It's not only position. When you talk about a particle in a fluid, there are two components of potential energy.
Because it's a trend, so you have to take into account the part before.
It's pressure. The second component is pressure. So basically here you have pressure acting on the particle. And you were right in saying it's accumulated from the movement before, because basically by moving down, the particle is pressing what? It's pressing up. It's pressing up water here and water here. And therefore this water, remember that inside a fluid and inside a wave, the hydrostatic laws applies, the hydrostatic law, singular. So I don't want to get into details of the hydrostatic law, but it means that if you have neighboring water that is higher, you have pressure generated by the neighboring water at a higher level that is transmitted through the fluid and goes here. So what is the result? Here you have the particle that is subjected by a pressure by the fluid, which is higher than the atmospheric pressure, and therefore the particle is not in equilibrium. It has energy, which comes from the pressure. But this is something that is not easy to understand. I tell you, when I told you that I started studying coastal engineering 3 years ago, and to understand this graph, it took to me to prepare this lecture a bit. So it's not an easy question. But what we need at the end of the story to keep in mind is that they compensate and they are equivalent. So it means that the max of kinetic energy is equal to the max of potential energy, which is fine, because we know that we admit for now that there is no dissipation, and we admit this because we know that there is very limited dissipation. If the energy of the wave is conserved, and you have some phases where you have zero kinetic, and some phases where you have zero potential, the total energy is conserved, it means that the max of kinetic is equal to the max of potential. So this is something that we need to keep in mind before computing the energy of the wave, because, you know, when you look at a computation, it's an analytical formula, so you have two ways to understand it. The way the mathematician usually uses is to understand the analytics. So he understands how to compute the integral. Once that he understood it, he's happy. And then there is the engineer. The engineer wants to understand the physics, wants to understand the process, what's going on. And then he's happy. So I'm now showing you the analytical relationship, but I just would like to make sure that you understand also the physics. Okay. And this is linked in my web pages, so don't worry about it. Now, this is the CLC formula. Don't be afraid. I'll also develop on the blackboard some of the computation. Don't get afraid, because it's very easy. And first of all, let's compute the potential energy alone, because it's a bit easier. And we know already that the total energy will be twice the potential. So let's compute the potential. And then we know that this potential energy is varying over the wave period, we can call it over the wave phase. The phase is evolving during the period. So you may say during the wave phase, as it is written in my web pages, but I could also have said during the wave period changes the potential energy. So let's compute the average during the wave period. So this is why, okay, so if I don't want to compute the average, I just want to assume. It's called EBB. EB is, we call the energy of the wave. EB. And if I say the energy of the wave, it's not enough. But let me tell you the further specification later. Okay? I call the energy of the wave EB. E stands for potential. So basically you have to get an integral, because any fluid particle has a different potential energy inside the wave. So, given that for varying the position of the particle along the vertical direction, I have a different potential, I need to compute an integral, and I extend the integral from minus dB. What is dB? Is the depth of the sea bottom with respect to the mean sea level. Okay, so I start from the sea bottom, and dB is the depth of water, so minus dB, if I take as 0 the position of the mean sea level, minus dB is the position of the sea bed. And I go up to what I call eta, which is the upper part of the wave. Okay, keep in mind that the upper part of the wave. Sorry? No, because it's evolving during the phase. So basically, this is the coordinate of the sea surface. So let me show you a wave. So this is eta. Okay? And then I already told you that I want to compute the mean value over the phase of the wave. Okay? Eta may be coincident with the crest, but in just one position of the phase. Okay? Okay, so let me introduce here the mass density of water, and then its potential energy. So let me put here gravity, and then the position of each fluid particle. I indicate it with the Z in the Z. Okay, and then let me take the mean. But let me subtract the potential energy of the wave up to the mean sea level. So let me, and this is not varying during the wave phase. So minus dB and 0 of rho g z in the z, rho g z in the z. Okay. This is energy above sea level. Okay? Because I want to take as a reference the mean sea level. If I wanted the energy with respect to the seabed, I should have not subtracted the second part. Okay. Now I can notice that I can, first of all, two things. First consideration, what kind of energy is this one? So what is the unit, for instance? Okay, so before considering the unit, let's try to understand what kind of energy we are talking about by intuition. So we know that potential energy is given by mass of the body. We are considering a fluid particle. Mass times gravity times position. Okay? Potential energy is expressed with respect to a reference plane, a reference horizontal plane, and it's given, if you remember my physics, for a body like this pen. If you want to know the potential energy with respect to the table, I have to compute mass times gravity times position with respect to the table. And the energy is released if I drop it. Okay? Until the table. If I wanted to compute with respect to the floor, position with respect to the floor. Here we are talking about energy with respect to what position in sea level. Okay, that's fine. Okay? But, again, the product is between mass, gravity, position. Here we have gravity, fine. Position, fine. Let's forget about the integral. The integral is just because we are talking about several bodies, several fluid particles along the vertical. Okay? So, gravity, position, mass density, there is a difference. So this is not an energy. It's an energy per unit volume. Because the mass is per unit volume. But then we are computing times dc, which means that I am integrating along the vertical. So the volume is along two directions, vertical, transversal, longitudinal. I am integrating along the vertical, which means that this is an energy per unit horizontal area. This is what you said. Area, yeah, and the area is horizontal. So if I consider a wave phase, the wave phase, you know, the wave runs along a transversal direction, longitudinal direction, and vertical. Okay, I am integrating over the vertical. It remains an energy per unit area and energy per unit area, horizontal area. So the units are fine, yes, for sure, but let's check. So basically, density is kilogram times, or let me say mass, not kilograms, because it may be, it's more generic. Mass times L cube. Acceleration of gravity is length divided by time squared, and z is length, dz is length. Okay, so this is mass divided time squared. Is the same thing as energy per unit area? Yes, it is. Because energy is force time acceleration times a shift. Okay? So energy, the unit of energy is a force. So the force is mass time acceleration which means again L divided time square, times, this is energy, times a shift L. So basically, energy is mass times L square divided by T square. What's the difference here? It's the L square, which means energy per unit area. Okay, now, second consideration of this expression here. So I delete here. Second consideration, I can split this integral in two parts. The first part is from the seabed to mean sea level. The second part is from mean sea level to eta. Okay, good. So let me rewrite it. BT is equal to integral between minus dB and 0 of rho g c in the z plus integral between 0 and eta of rho g z in the z average. Look, I'm not averaging here because there is nothing to average. Everything is, this is constant. For varying eta, varying the wave phase, it's constant. Okay, and then minus integral, what is written above here, minus dB and 0 of rho g z in the z. So I can, these two compensate. Okay, now, oops. Just 1 second, because there is also the screensaver. Okay, so let me rewrite about here. This is just the integral. I changed the color. 0 of rho g z into z and average. And what we can do now is we can compute the integral. Actually, the result of the integral is 1/2 g z squared computed between 0 and eta average equal to 1/2 g eta square average, which should be the same that is there. Yeah. Now, this is easy to understand. Of course, this development is something that I like to ask you at the exam. Otherwise, I wouldn't spend so much time working on the blackboard. And also I like it because it's one of the few relationships that can be derived analytically, that have a physical basis. And therefore this is the reason why I'm spending time, because I think also the concept is extremely important. Okay, now you have to trust me if I tell you, and you can try on your PC with an Excel sheet, if I tell you that, first of all, this is an average, I can bring the constant out of the average. So this is equal to 1/2 g average of eta squared, average along the wave phase. Okay, and now you have to trust me if I tell you that the average of eta squared is equal to 1/2 A squared, where A is 1/2, was I correct? Yeah. And where A is wave amplitude. And therefore, it's also, we can say that ED, P, is equal to 1/4 G A squared, which is also equal to, given that A is equal to HB, yeah, HB divided by 2, where HB is wave height, we can write that this is equal to 1/16 G HB squared.
Sorry, what is the meaning of the passage in the up part? Up, right?
This
yeah,
one?
From yeah, this.
From here to here.
Yeah, from here to here.
This is an average, and you can bring constant quantities out of the average. So you see that the average is now limited only to it.
Okay, so after 1/2 is a G. There is a G.
Yeah, it's a G. Yeah. So this is potential energy, and if we want to compute the total energy, what should we do? Yeah, that's easy. Just twice it. No, that's fine, because, no, it's fine. I felt uncomfortable.